Hello guys, so next part of your presentation on materials, you need to start explaining to me the difference between a ductile and brittle material. Now, very simply, a ductile material, something that's nice and bendy. So I'm going to take this Mauam as an example, something that I can bend quite easily. It will bend out of shape, but it doesn't snap, okay? If I sort of stretch it, it will snap there. So that's ductile. So think about the construction materials that are ductile, bendy construction materials. We obviously don't want construction materials that are too bendy because we don't want to be walking around on trampolines. Now, we've then got our brittle material. Now, concrete is a brittle material. It seems very strong, but actually with the loads we put under it, it's quite brittle. So if I take this biscuit and I bend that, we can all guess what's going to happen. It's not going to bend much, there's not going to be much flex, okay? So what happens, and it crumbles very quickly. So that's our brittle material. Okay, so let's put that into concepts of construction. So, as we said, concrete, brittle material. And you can see here how this concrete beam has cracked under load. It doesn't deal with tension very well. Now remember, we don't have to stretch concrete to put it under tension. Remember our 3-point loading where we said that if we apply a load from above on something, it's going to flex out of shape. Remember, we did the thing with our fingers where we went like this and we had tension on the bottom. And if you look at this beam, it's kind of breaking out at the bottom. So if you had a timber beam or something like that, where would you expect to see the splinters? You can quite often see this in your house. If you look up at the ceiling downstairs, if you've got a plasterboard ceiling, and if you've got flexy sort of timber joists and they flex too much, it will start to push the nails or the screws that hold the plasterboard in place out, and you'll start to see cracks appearing in your house. It's not a problem, and we can have a certain amount of flex in our houses. We'll come to that in a bit. Okay, so brittle materials. Concrete is a brittle material and it does not deal well with tension. It cracks. So we then have ductile materials such as steel. Steel is ductile and it copes well under tension. Okay, so we can see this real obvious example here. We've got Hammersmith Bridge just up the road. So all these cables coming down here in tension. This long one would be in tension as well here. Okay, we can also see this sometimes in construction. We use struts or cables, cable masts. This one's just holding a canopy up above a building. We don't see this a lot. This puts a tremendous force in this area here. So it's not a very common way of building. So what we need to do is we need a material that's good in both compression and tension, especially when it comes to that 3-point loading, so it can resist that compression along the top of the beam and tension along the bottom of the beam. So what we do, we put steel, we call the steel rebar, okay? So rebar, just shortened for reinforced bar. This is quite a rough steel that we put inside concrete. Now we don't drill a hole and put it inside. We pour the concrete as a liquid around the steel, okay? And we'll come to in more detail later on to how we do that. So with the two materials together, now we've got a material that's good in both tension and compression, and we can call those kinds of materials composite materials. Okay, next thing you need to explain to me is Hooke's law. I'm going to put a separate video up about Hooke's law as well, someone explaining it much better than me. But Hooke's law you will have covered in science, hopefully. This is the idea that when you stretch an object, it returns to its original shape. I'm just looking around for something to stretch. Here we go. So if I've got something flexible, if I bend it, it goes back to where it started from. Okay, so normally we would do this with a spring or something. That's the classic science experiment. But in a construction environment, we want to know a floor, for example, will it flex and will it go back? Now, we don't want to be walking on trampolines, we said this earlier. So we need to understand, Hooke's law is important to us in construction because we need to understand how our materials are going to behave. So timber, for example, has a certain amount of flex and it returns back to where it started from. If it returns back to where it started from, it's still within its elastic limit of proportionality, okay? So a rubber band or something like that. Now, if you take a rubber band and you really stretch it, it will stay longer. So that's gone into plastic deformation. We don't want that in a building. Otherwise, we'd have sort of bowed floors and things like that. but a certain amount of flex is acceptable. Multi-story car parks, big concrete floors. We'll look at how we use deflection, a thing called a deflection header you could look up, where we build big concrete apartment blocks, but we allow those floors to flex ever so slightly. It's only a small amount, but we need to account for that flex. So that's where Hooke's law comes into this. So like I said, I'm going to post up some other videos as well to help you do your presentation. Once again, don't go crazy on the explanations. What you've done so far is really good. Just get the basics, and the really important thing to get the higher grade is you back it up with some evidence and you use real construction scenarios, images, diagrams, and explain what's going on in this picture. This is where we'd see tension. This is where we'd see compression. This is why we need to know about Hooke's law in construction. Thank you very much, guys.